Today we will find the electric field from a line of charge. But first let's review the electric field from a point charge. Here's a point charge. Let's say it is a positive charge plus Q. And we want to find the electric field at the point P over here. And this point P is a distance r from the charge Q. The electric field for a positive charge is directed away from the charge like this. And the magnitude of the electric field is E equals 1 over 4 pi epsilon 0 times Q over R squared. What happens if we have a macroscopic charged object? Here's a macroscopic charged object, also called a continuous charge distribution. Now, to find the electric field from the macroscopic object, we divide it into small elements of charge, dq. So here's one of the dq's. And this element of charge dq is going to produce an electric field. Let's say we want the electric field over here at the point P. And dq, if it is positive, will produce an electric field pointed away from dq, and we'll call that electric field dE. And if we want the electric field from the entire charged object, we have to sum all the dq's. That summation is an integration. So we can write this. E equals, this is the magnitude of the charge, the integral of the dE. Well, we'll make it a vector. The integral of the dE. And the dE has a magnitude of 1 over 4 pi epsilon 0 dq over r squared, where r is the distance from dq to the point P where we want the electric field. And the direction of dE is in the direction of the unit vector, r hat, a vector of magnitude 1 which points along the line between dq and the point P. So we can write our summation like this. 1 over 4 pi epsilon 0 dq over r squared times r hat. Now we will apply this formula to the case of a line of charge. So we have a line of charge which is of length L, and it has a uniform linear charge density lambda. Lambda is the charge per length. And we want to find the electric field at a point along the axis of the line of charge at a distance a from the end of the line. Let's first draw our coordinate axes. Here's our x-axis, here's the y-axis, and now let's draw our line of charge. Right here, here's our line of charge. It goes from the origin to x equals L. So this length here is L. And we want to find the electric field at the point here. This is point P. And point P is the distance of A from the end of the line of charge. Now, to solve this problem, we divide our line of charge into little microscopic lengths, dx. So here's an example. Here's the dx. And that dx is located at a distance of x from the origin. And the charge in that length of dx is dq, which is given by lambda, the charge per length, times dx, the length. The electric field produced by dx for a positive charge is directed along the x-axis to the right, and we'll call that dE. So let's write down what dE is. dE is 1 over 4 pi epsilon 0 dq over r squared, where r is the distance from dx to the point P. So it's this distance here. Looking at this diagram, we can see that r is equal to L plus A minus x. So then we have this. dE is 1 over 4 pi epsilon 0 lambda dx times L plus A minus x squared. So to find the net electric field, we have to sum all of the dE's throughout our line of charge, and we'll get the following expression. E equals the integral of dE, which is the integral of 1 over 4 pi epsilon 0 lambda dx over L plus A minus x squared. And we must integrate from x equals 0 to x equals L. So our limits of integration are 0 to L. To solve this integral, we will use u substitution. So let's say that u equals L plus A minus x. If we differentiate this, we get du equals negative dx, because L and A are constants. So then let's rewrite our integral, getting rid of the x's and replacing them with u's. And we get the following. First of all, we have the constants. Lambda over 4 pi epsilon 0 integral of negative 1 over u du, where x equals 0 to x equals L. The integral of negative 1 over u du is just, 1 over u squared. The integral of negative 1 over u squared du is just 1 over u. So our integral then becomes E equals lambda over 4 pi epsilon 0 1 over u x equals 0 to x equals L. Now putting in what U is, lambda over 4 pi epsilon 0, 1 over L plus A minus X from 0 to L. And this becomes lambda over 4 pi epsilon 0, 1 over L plus A minus L minus 1 over L plus A. And this becomes E equals lambda over 4 pi epsilon 0, 1 over A plus 1 over L plus A. Let's get a common denominator here. It becomes, the common denominator is A times L plus A. So it's L plus A, just a minute. This is a minus sign here. Erase. Minus. So L plus A minus A over A times L plus A, which is lambda over 4 pi epsilon 0 L over A times L plus A. So this is the electric field at a distance A from the end of the rod along the axis of the line of charge. What happens when A goes to infinity? Let's see. If A goes to infinity, L over A times L plus A goes to 0. So we can write limit A goes to infinity of E is 0. That is what we expect, because when A goes to infinity, this line of charge looks like a point charge. And we know that the electric field of a point charge is 0 at an infinite distance from the charge. Let's now continue with the same line of charge of length L. But now let's find the electric field at a point along a bisector of the line at a distance A from the line. Let's draw our coordinate axes. X, Y. And let's draw our line of charge right here. It's along the x-axis, and like this. Oh. And we will put one end at negative L over 2 and the other end at L over 2. So the y-axis is along the bisector of the line. We want to find the electric field at point P on the y-axis. And it is a distance a from the line of charge. As we did before, we divide our line of charge into little lengths of charge dx here's a dx, and this length of charge dx is at a distance of x, a distance x from the origin. Now the electric field produced at point P from the x is in this direction, right there. And we'll call that dE. And this distance here is r. And this is a right angle triangle. Now there's another dE produced by the strip of charge dx on the other side of the y-axis, and it's a dE of the same magnitude. It's also a distance r from the charge dx, and these two dEs have the same magnitude, but they have x components which are in opposite directions, so the x components add to 0. And you can do that along the entire line of charge, and you'll see that the net electric field is going to be in the y direction. So we only have to look at the electric field in the y direction. The electric field in the x direction is 0 because they all cancel out. Now the length dx has a charge dq, which is lambda dx, the charge per length times dx. Let us now write down the expression for dE. dE equals 1 over 4 pi epsilon 0 times dq over r squared. R squared is given by this right angle triangle. Just use Pythagorean theorem. R squared is a squared plus x squared. So we'll put that into our expression. 1 over 4 pi epsilon 0 lambda dx over square root a squared plus x squared. Now we want the y component of the electric field. So let's look at this angle theta here. There's our theta, and there's a theta up here. So here's theta down here. Okay, so the y component, dEy, is dE cos theta. If we look at this triangle here, cos theta is adjacent over hypotenuse using trigonometry. So adjacent is A, hypotenuse is R. So it's A over r, which is square root a squared plus x squared. So let's put both of these things, the cos theta and the dE, into our expression for dEy, and we get lambda over 4 pi epsilon 0 times dx over square root a squared plus x squared. Oh, I'm sorry. Just a minute. We have to get rid of this. This is not, get rid of that square root. R squared is a squared plus x squared in this expression. So I'll get rid of this. So there's no square root there. Hopefully you caught that before I did. That means you're paying attention. Thank you very much if you did. So a over square root a squared plus x squared. So let's put it all together. This becomes lambda a over 4 pi epsilon 0 dx over a squared plus x squared to the 3/2. Because a squared plus x squared to the 1 times a squared plus x squared to the 1/2 is a squared plus x squared to the 3/2. Now, to get the total electric field, the x components are 0, so we just sum all the dy's. Integral of dEy. And the electric field is going to be in the y direction. So integral of dEy. So let's put in our things here. Let's take out the constants. Lambda a over 4 pi epsilon 0 is a constant. So we'll take that out of the integral. Lambda a over 4 pi epsilon 0. Integral of dx over a squared plus x squared to the 3/2. The limits of integration, we go from negative L over 2 to L over 2. So here, negative L over 2 to L over 2. So there's our integral. Solve that integral and we can find the electric field. Now I'm going to change these limits of integration. I'm just going to go from 0 to L over 2. I'll just do half of it and multiply by 2. So let me write it like this. E equals lambda a over 4 pi epsilon 0 times 2 from 0 to L over 2 dx over a squared plus x squared to the 3/2. Let me change that thing. Erase. 2 over 4 is just 2. 2 over 4 is 1 over 2. So I'm going to change that to lambda a over 2 pi epsilon 0. So let's solve this integral to get the electric field. So our integral is this. Integral of 0 to L over 2 dx over a squared plus x squared to the 3/2. To solve this integral, we need to use trigonometric substitution. The way to approach this is to draw a triangle. A right angle triangle. This is theta, this is a, this is x, and this is a squared, square root a squared plus x squared. So from this triangle, we see that tan theta equals x over a. Let's differentiate. Sec squared theta d theta equals dx over a. So now we've got dx in terms of theta. The next thing is to find a squared plus x squared to the 3/2 in terms of theta. Well, again, let's look at our triangle. Cos theta is adjacent over hypotenuse. That's a over square root a squared plus x squared. Well, we want a squared plus x squared to the 3/2. So let's cube this whole equation. We get cos cubed theta equals a cubed over a squared plus x squared to the 3/2. So this is what we have. 1 over a squared plus x squared to the 3/2 equals cos cubed theta over a cubed. Now, let's put these things... oh my goodness. Something disappeared here. This is a strange thing. I wonder how I go back. Oh, there we go. Lucky we didn't miss the whole thing. Oh, we did this. Here we are. So we have this thing here and this thing here. We'll take these two things, put them into our equation up here. Okay, so we're going to get this thing becomes integral of a sec squared theta d theta times cos cubed theta over a cubed, which is one over a squared. Now, sec squared theta is 1 over cos theta. So we have cos cubed theta over cos squared theta, which is just cos theta. So integral of cos theta d theta, and integral of cos theta is sine theta. So it's 1 over a squared sine theta. And then let's put in what sine theta is from this triangle right here. First of all, let's erase something. Let's erase this stuff here. So from our triangle, we see that sine theta, opposite over hypotenuse, x over square root a squared plus x squared. So our integral then becomes 1 over a squared x over square root a squared plus x squared. And we're going from x equals 0 to x equals L over 2. I should have put it here, just to be precise. X equals 0, x equals L over 2. X equals 0, x equals L over 2. Here, x equals 0, x equals L over 2. Okay, so that is L over 2 divided by square root a squared plus L squared over 4 minus 0. Now let's multiply this first term by 2 over 2. Because I want to get rid of this 4 in the denominator. So this becomes L over, now we bring this 2 inside the square root. So it becomes a 4. Square root 4a squared plus L squared. So that's the integral. And now let's go back. So what is the electric field going to be? Electric field is, let's just go back here. Lambda a over 2 pi epsilon 0 times that integral. Lambda a over 2 pi epsilon 0 times, oh, I forgot the 1 over a squared factor. 1 over a squared. So 1 over a squared. Okay. Times 1 over a squared, L over 4a squared plus L squared, which is lambda L over 2 pi epsilon 0a times square root 4a squared plus L squared. So let's write our final answer. First of all, let's make some space. Let's get rid of all this stuff. So our final result, the electric field equals lambda L over 2 pi epsilon 0a square root 4a squared plus L squared times vector j, unit vector j. So that is the electric field. Here's a question. What happens when L becomes infinite? L goes to infinity. When L goes to infinity, we have this factor, L over square root 4a squared plus L squared. What happens to that? Well, that's just going to go to L over L squared, when L is very large, is much larger than 4a squared. So we can ignore the 4a squared. It becomes L over square root L squared, which is L over L, which is just 1. So limit as L goes to infinity of electric field equals lambda over 2 pi epsilon 0a unit vector j. Now let's look at another way to solve these problems. Oh, this is a very exciting way, and we have a visitor here. This is Giselle the Gazelle. Giselle wanted to visit us on this part of the presentation because we're going to be doing Gauss's Law. And Giselle really likes Gauss's Law. So let's give Giselle a round of applause. Thank you very much. Giselle, tell us why you like Gauss's Law so much. That's right. I agree. Giselle likes Gauss's Law because it is much easier to use. So let's see how it is so much easier to use. First of all, let's just write down what Gauss's Law is. So this is Gauss's Law. Integral of E dot dA equals Q inside over epsilon 0. So what we do here is we have some surface. It's called the Gaussian surface. And we find the electric field. We do this E dot dA all along the surface. This circle here means the integral is over the entire closed surface. So that integral over the entire closed surface, E dot dA, that's called the electric flux, phi. And that equals the charge inside the surface divided by epsilon 0. So this is whatever the charge is inside, the net charge. Just add up all the charges together, and that gives you the charge inside. Now, Gauss's Law is easy to use if you can find a surface for which the electric field has a constant magnitude on that surface. And that doesn't work for all situations. For instance, let's consider our line of charge. So here's our line of charge of length L. And the electric field around this line of charge, it's perpendicular to the line of charge, right at the line of charge, but then it's going to curve. So the electric field lines look something like this. They're straight, but then they start curving around. So you have something like this. So electric fields are curving around because when you're at an infinite distance from the line of charge, it has to look like a point charge. So those electric field lines have to curve around. Now this makes it difficult. I'm going to erase this. I don't like this electric field line. Let me erase that one. This makes it difficult to find a surface, the Gaussian surface, on which the electric field is constant. For here's an example. Let's draw a Gaussian surface. Say we're going to work with a cylinder. We'll have a Gaussian cylinder. That's our surface. It looks something like this. And it is we can't find a cylinder for which we can easily find this integral, because E, look at the E here. Here's E. E curves in this part, and dA is always perpendicular to the surface. So E dot dA, there's an angle between them. But here, E is just straight there, and dA is also straight. They're parallel here. But over here, there's an angle between E and dA. So we don't have a surface for which E dot dA is constant over the whole surface. So we can't use Gauss's law for a line of charge of finite length. But if the line of charge has an infinite length, we can use Gauss's law. let's draw a line of charge of infinite length. So it looks like this. There's our line of charge of infinite length. It's not drawn to scale, of course. And now let's draw the electric field lines. For a line of charge of infinite length, the electric field lines are always perpendicular to the line of charge. It looks like this. No matter how far we are away from the line of charge, the electric field lines are always perpendicular to the charge, because the line of charge is infinite. And so now, if we do our Gaussian surface, we can take a cylinder like this, and now over the surface of our cylinder, the electric field always has the same magnitude, and it is in the same direction as dA. And dA is always normal to the surface. No matter where we are on the surface, E is always perpendicular to the surface, to the curved surface of the cylinder. What about at the ends? At the ends, dA is perpendicular to the surface, but E is parallel to the surface at the end. So for this end and for the other end, E dot dA is 0. And E is constant on that curved surface. So if we do this integral, E dot dA, it is the E dot dA for the curved surface plus on the two ends, left end at 0, the right end at 0. So we can just do this integral on the curved surface, and then we can find that integral easily. So let's show how that can be done. Let's come back to our line of charge. So here's our line of charge of infinite length. Here's our Gaussian surface. It's a Gaussian cylinder. So there's E. And dA is always parallel to E throughout the surface. So here at the bottom, and at the two ends, E and dA are perpendicular. So when we do our integral, E dot dA, it just becomes E times the dA of that curved surface. And because E is constant on that curved surface, constant magnitude. So the area of that curved surface, and let's say in this problem the radius is A, because we want the electric field at a distance A from the line of charge. So that surface area is the circumference of the circle, 2 pi A, times the length of the Gaussian surface. So now we have to have a length. So let's say our length is S. So 2 pi A times the length. And that equals Q inside over epsilon 0. So Q inside, we have Q in is charge per length times the length S. So it's lambda S over epsilon 0. Now look what cancels out. S cancels out on both sides. So we have E times 2 pi A equals lambda over epsilon 0. Let me erase this. there. Lambda over epsilon 0, or E equals lambda over 2 pi epsilon 0 A. This is what we found before for the rod of length L when we let L go to infinity. We got the same result. So now we've seen how to find the electric field from a line of charge using integration for a continuous charge distribution and by using Gauss's law. And we can use Gauss's law when we have the right symmetry. And for our case, we had to have an infinite line of charge. I hope you enjoyed this presentation. Please be sure to like and subscribe, and leave any comments in the space below. Thank you for your attention.